Hey guys, welcome back to Zenkaya, and today we are going to start with machine learning. So let's start without wasting time. The first algorithm we are going to see, that is linear regression. But before going to linear regression, we will just see some classification of AI and where does ML comes, where does deep learning comes, where does Gen AI comes. We'll see that classification, and we'll jump into ML classification again, supervised, unsupervised, and then we'll see the linear regression. So basically in this video I am focusing more on math intuition. All right, so I see that many people do ML from the approach of coding. They do code, they run code, but they lack one thing, that is the math, the understanding of math behind the process scenes. So in this video we are going to go in depth, especially maths. All right, so let's start the video. So the first thing, as I told you, we are going to see is AI. This term AI, in simple words, it is nothing but automation, right? Automation, the things we can do as a human beings. What if we can automate those things? Example, self-driving car. Some more example, spam detection. Spam detection. Netflix. In Netflix, we see movie recommendation. So these are some examples of AI. When we say AI, we can understand by this application. All right. So let's come back to the classification, how we can classify AI. All right. This box, imagine it as AI. Okay. So I'm trying to explain it in the form of set. Okay. Set diagram. So this big box is AI. Then let's say the smaller box, it will be ML. And inside this, a part will be known as DL, deep learning. Inside this, a part, let's say Gen AI, and many more inventions or discoveries are going on. But this is the main part. Or one more thing, where does data science comes? So let's take another part which covers all of it. So this part we can say it as data science. So in this way you can understand the classification of AI. AI is not only machine learning. Apart from machine learning, there are many AIs, let's say robotics or embedded AI. So those doesn't come under machine learning. All right. So in this video, we are going to see specially about machine learning. Let's get into it. Machine learning. So the first thing is classification. We need to understand how machine learning is classified, what are the types of machine learning algorithm. Then we will look into the first algorithm, that is linear regression. So let's divide it. First, we can divide it as supervised learning, and second is unsupervised learning. All right. In supervised, we are feeding data. Let's say we are giving some data set to a model. Let's say dog's picture we are giving. Along with that dog, we are sending a tag that it is a dog's picture. All right. So whenever we use some data set, we are sending those data. Along with it, we are sending that this is a dog. So basically we are supervising the model that this is a dog. So understand, next time when I send this same picture, you identify it as dog. All right, that is what it means. In unsupervised, we send one picture, but we don't send them the tag that it is a dog. We just send them the pictures. That's it. Simple. So next, in this supervised learning, again it is divided into two parts. One is regression and one is classification. We'll see one by one, regression and classification. So exactly what is regression? Regression is nothing but a type where or an example where we need a continuous learning. Okay, continuous graph. Let's take an example. Let's say if I study for 3 hours, what will be my marks? If I study for 4 hours, what will be my marks? So depending on a line, a continuous line, where even if I study for 3.5 hours, I will get some prediction. All right. So basically it is continuous. It has continuous values. It is not discrete. All right. It is a continuous. It has continuous values. Next is classification. This classification, again, you can divide it into two parts. One is binary and one is multi. So by the name itself, we can understand one is binary classification. Let's say I am sending a picture to identify whether it is dog's picture or not. All right. So yes or no. Or let's say if I study that much, will I pass or fail? So pass or fail. Binary situation. Okay. Binary condition where you get only two outcomes, not more than two outcomes. Multi class in the other hand, it is nothing but multiple conditions. For example, grade system. If I study for 3 hours, I'll get, let's say, C. If I study for 40 hours, I'll get, let's say, D. If I study some more hours, let's say I'll get B. So in which category it is exactly falling? So it has multi-class. All right, depending on the question, depending on the data set, it have to predict that whether it is B, C, D, or A. All right, this is called multi-class. Next comes unsupervised learning. In this unsupervised learning, we do two things. One is dimensionality reduction, and one is clustering. So what exactly we do in clustering and what exactly we do in dimensionality reduction? In clustering, we don't need any answer. Okay, we don't expect any answer. Let's say there's a graph that represents a customer. So let's say this is one type of customer who buys, let's say, rice. Okay, and another type of customer who buys biscuit. All right, so these two are categorized into two parts. We are just categorizing. This is one category and this is one category. So this is known as clustering. All right, this basically are used in analysis of data. All right, let's say Amazon. In Amazon, which kind of category of people are buying things? Let's say rich people are buying a product A, medium poor people are buying category B. So basically they are doing what? They are categorizing. All right, this is called clustering. In dimensionality reduction, it is a process of reducing the features, reducing the features, keeping in mind that the important features are kept and all the unnecessary features are removed. Example, if it is having 100 features, then it will reduce to 10 features, keeping in mind that the model is still working. All right, this is called dimensionality reduction. I hope you have understood this particular classification. This classification is very, very important. So now let's get into a first algorithm, that is nothing but linear regression. It is a part of regression. So again, two parts will be there, linear regression and logistic regression. We'll see those. But first, let us complete linear regression. All right, I told you that linear regression represents a continuous values, right? When a scenario where we can predict a continuous values from an input. So let's take an example, age and weight. So for this age 18, let's say weight is 60. So somewhere here. Again for 19, age will be 67. So we have to predict that. All right, we have to predict the lines. So that line have to be a continuous line. So in simple word, linear regression will represent a continuous line in a graph where for any value of input, we can predict a particular output. All right. So let's look at the model. Let's first understand, before jumping into the linear regression, first understand how ML model works. Okay. If we take a classic model that is nothing but, let's say, any algorithm, how it works. So you pass input and you write some algorithm and it will give you output. All right, this is how model works. But in ML, in machine learning, how it works is, machine learning, we train the model. So first what we have to do is, it does not learn by itself. If you are thinking that it is learning by itself, no, it does not learn. It's just that we are training enough data to make it understand or to find the pattern. I would say to find the pattern. This is Okay, so this is a model. So in this is, here it is a model, here it is a model. In this model, what we try to do is we try to send one input, and at the same time we'll send a output also. All right, we'll send some input of, let's say, pictures of dog, cats, whatever is there. Let's say we are sending some pictures, and at the same time we are sending a tag also, that this is a dog's picture, this is a cat's picture, and we are expecting some pattern, that this model will try to find that pattern and it will give me the algorithm, or we can say pattern. We are trying to find the pattern. So once it gets the pattern, then after that we can send one input and it will give us output. So at first you need to train the model. Without training the model, it won't give us, automatically it won't give us the result. All right, I hope you understood. So let's move to the next part, the linear regression. Linear regression. I will take one example to make you understand. Let's say X is house size. This is some input, and Y is house price. So let's say 20 size, 20 size, and house price will be 1 lakh, let's say 1 lakh. All right, I'll be sending many data like this. 30 size, 2 lakhs. I'm just assuming some random value. Okay, so let's say this is here, this is here, and it have to predict the best fit line. And according to that best fit line, whenever a new data comes, you have to predict that, okay, the answer is here. So according to the size, we have to predict the price. So if the size is this, the price is this. All right, this is how it works. So okay, this is a theoretical understanding of linear regression. Now let us try to understand using mathematical approach. All right, that is very, very important here. Here we are focusing more on mathematical intuition, how exactly the formulas are made and how it is finding the solution, how it is finding the pattern. All right, humans has always been curious about this, that how our human brain works. All right, how we can think. So let's start with that, the hypothesis, the hypothesis function, the hypothesis function. So there have to be some formula, right? There have to be some formula regarding this linear regression. The formula we use is, it is a very popular formula, that is y equal to mx plus c. This is a very popular formula of straight line, a straight line formula. So here some terms are there. This m is known as slope and this c is known as intercept. So if you don't know what is slope and what is intercept, let's say this is graph. In this graph, this is x, this is y. So at x equal to 0, which point it touches at y, that is known as intercept. So for example, if here x equal to 0, at this point where y intersects, so let's say y intersects at 1, so intercept will be 1. All right, if I this at 0, if the line intersects at 2, then intercept will be 2. So at x equal to 0, at what point the line intersects at y, that is known as intercept. Slope, what do you mean by slope? Slope is nothing but with the change of x, with the change of x, unit change of x, how much y is changing, that is nothing but slope. So for example, let's say this is a line. In this line, when we move towards x, what is the change in y? What is the change of y with respect to change of x? This is known as slope. So when we are changing 1 unit of x, let's say this is also changing 1 unit of y. So this is known as slope. So m equal to 1 means when we increase 1 unit here, y will also increase 1 unit. All right, I hope you are clear with slope and intercept. This is very, very important. As we go on, you will understand the importance of this particular formula. All right, often we see that it starts from a basic formula and it gets more complicated. All right, so this formula we will refer to and we will be creating a similar formula that we will call it as hypothesis. All right, h theta of x, so basically y, this is y, I'm just naming it different, nothing else. Y equal to mx plus c, right? Theta 1 x plus theta naught. All right, I'm just changing the name. This we will be taking as hypothesis. This is a function we'll be taking or we'll be using throughout the algorithm. This is the hypothesis. All right, here theta naught is a intercept and theta 1 is a slope. It is similar to m and this is similar to c. All right, very important. All right, so this is called hypothesis formula. This will be using throughout the algorithm. Now you would have one curiosity that again this formula, how we can find out or how to adjust it. So if you look at this formula, there are two parameters that we can tweak. All right, x is nothing but an input. If you see x is nothing but an input. All right, x is an input. So two parameters we can change is theta naught and theta 1. Theta naught is intercept and theta 1 is slope. So using these two parameters, we will tweak these two parameters in such a way that we will get the best fit line. So what is our aim? Throughout the algorithm, our aim is to fit a best or create a best fit line. This is our aim or this is our goal. All right, this is our goal. So how we can create? Basically, we have to change. We have to keep on changing this two, theta naught and theta 1, and we have to analyze whether the error is minimum or not. All right, error should be minimum. Error means what? I am predicting a number. Let's say my prediction is 4 and the real prediction is 3. All right, what is the difference? The difference is 1, right? The difference is 1. So like this difference we need to minimize as much as possible. All right, basically you can say reduce the error or reduce the difference. All right, so now you should understand how to reduce the error that we will see. All right, that is known as basically cost function. Again, one new formula we will be using that hypothesis formula only. We will be creating another new formula. So this particular function will find us what? This will find us how wrong we are or how right we are. How wrong we are. So any line we can take, but that line is best or not, that is what it is decided by cost function. All right, so first let me write down the formula and then we'll understand exactly each and every terminology, each and every terms, why it is written. All right, so here we will be denoting this cost function by j theta. All right, this don't think about much why we are using j, why we are using h. These are some terminologies. All right, in mathematical terms these are some functions. We are just representing one function, cost function. All right, here j theta, it is nothing but cost function. So j theta equal to 1 by 2m summation of I equal to 1 till m is nothing but total number of data sets, and here predicted predicted value minus actual value to the power whole square. This is the formula of cost function. I'll get back to each and every term, but here you need to understand that this is the formula. Now the first question you should be asking is why this square? Why this square? So this square we are using just to avoid or ignore the negative and positive. So imagine here in this diagram, okay, I'll create one more example here. Let's say our data points. Okay, few data points are there. Data points 1 1, 2 2 and 3 3, x1 y1 x2, y2, x3, y3. These are data points. Okay, 3 points we have. So we just need to fit, this is x, this is y, 1, 2, 3. Here also 1, 2, 3. So we need to fit this points. So where will fits 1, 2, and 3? So when we fit this line, what will be the best fit line? The best fit line is obvious, that whichever line passes through all of this is the best fit line, right? So here error is 0. Why error is 0? Because all the points are intersecting this particular straight line. All right, there is no error. So when we give another input, let's say 4, then output will also be 4. So it is basically predicting a answer for us. All right, this is what it means. Now it is not obvious that all the lines will be falling in the same straight line. In real world scenario, it is not possible. All right, the data will be somewhat like this. Let's say one data is here, one data is here, one data is here, one data is here. So our aim is to get the best fit line out of those uneven points. Okay, so let's say these are the points and my best fit line is this straight line, black color line. All right, so in this case, my error, this is my actual and this is my prediction. This is my actual and this is my prediction. This is my actual and this is my prediction. Here this is the prediction and this is actual. All right, so this errors, what it will do, this is positive, this is negative. So it tries to cancel each other. So in order to avoid that cancellation, what we do, we square it so that everything becomes, the negative cancels each other and we just get the positive value. All right, that is why we use this square. And one more reason is there, that we want a curve. Okay, we want a curve that looks like this. So I'll be explaining this curve, a curve like this, parabola, or let's say hyperbola. Okay, a curve like this. So we know one thing, that whenever we use some square, we will get a convex function. So I'll come back to this point. For now, just understand, we want to, or we try to create a curve that is convex in nature. All right, that is why we are using this square. All right, so this is the formula. Let me here write the full formula. This is not the full formula. So here, let me reduce it. 1 by 2m. Why this 2? I'll tell you. So this 2 we use just to cut out during a derivation. All right, let's say x square is a equation. If you derive this, if you do d of dx, what we will get? We will get 2 of x and dx of dx. This is what we get, right? So this 2 and this 2 will get cancelled out. So basically this square and this square, this 2 will get cancelled out. All right, that is the reason we are giving this extra 2, so that it does not add any extra value. Whatever value we are getting, we are cancelling it out so that it matches the real value. All right, this is why we are giving 2. And this m means it is a average or mean, you can say. All right, we try to find many errors. All those errors, we will try to find the average. How we find average? So basically it is a total sum divided by total number. This is a basic formula that we use to find average, right? Average. So here also we use the same thing. We find the errors and then we divide it by total numbers, that is m. M is the total number of data sets. All right, so here predicted. This predicted formula I already told you, it is represented by h theta of x. So this h theta of x, it is nothing but summation of I equal to 1 m h theta of x of I minus this actual value is nothing but y. Okay, y cap. I'm just writing it as y cap square. So this is my actual formula of j theta. This represents cost function. So I explained you each and every term. Don't be confused. This formula will be using it again and again in the algorithm in the later stage. All right, so I'll again repeat it. It is very simple. What we do, this 2 is added just to remove the cancellation part of positive and negative, and we want a convex function. That is the reason we are using square. And here we are adding this 2 because of derivation. When we do derivation, this square 2 will come down, so it will cut out itself and we don't get any extra value. And this m is because of average. We want average, right? We don't want a particular value. All the error we have to do what? We have to find the average. So for finding average, we are dividing it with m. As simple as that. Now this summation, this is the predicted value. This is what? Predicted value, and this is actual value. So predicted minus actual will find the difference, and then we are squaring it off so that negative value will become positive. So this is how we can find the cost function. So now you can ask, what is the use of this cost function? All right, what is the use of this cost function? So I will try to plot a graph and I'll try to walk through you with an example so that you understand this better. So let me first write down this cost function here, cost function, and let me write down the formula. What is the formula? J theta is, J is a function, cost function as we say, it represents a function, and here it is 1 by 2m summation of I equal to 1 to m and predicted minus actual whole square. All right, this is the cost function that we are going to use. This is the cost function we are going to use. All right, in this, so now we will see an example. Okay, let's see with an example what exactly this cost function helps us to find. So I showed you this graph, right? This graph we are going to look at now. So this formula we are going to use. Let's take an example where, again same example I'll use. These are data sets. Let's say these are data sets, supervised data sets. So 3 points are there, 0.1, 0.2 and 0.3. All right, so if I plot this in a graph, it will look something like this. Okay, x axis, y axis, 0.1, 0.2, 0.3, and this is 0, this is x, this is y. All right, so in this I showed you already that what will be the best fit line. Best fit line will be somewhat here. All right, but in this case, let's say we don't know what is the best case. Okay, what is the best case? We don't know. Let us assume with a random slope, and then we will try to get into that best fit line. Okay, we are not directly getting into the answer, but we are just trying out random values, and then we will try to get into that minimum value slowly. All right, so let's check with an example. So in this formula, we will try to do some experiment. So in this experiment, first let us try to find the hypothesis. So the formula that we use is h theta. This predicted, first we have to find, right, this prediction. First we have to find this prediction. So this h theta, what is the formula? Formula is theta 1 x plus theta naught. Theta naught is intercept, theta 1 is slope. All right, so in this case, what we'll assume is, we are just assuming, again we don't know where the intercept will be or where the slope will be. We are just assuming that the intercept is 0. All right, that means it passes through the origin. It passes through the origin. So let theta 0 be 0. That means what? It passes through origin. So now in the first case, let's assume again theta 1. So we have assumed theta naught. So let's assume theta 1 as 1. What do you mean by 1? 1 means slope. Slope is 1. So slope 1 meaning when x is increasing by 1 unit, y will also increase by 1 unit. Okay, so our slope will look something like this, a straight line passing through all the points. So basically by a diagram we can understand that this is the best fit line, but let us assume we don't know whether it is best fit line or not. Okay, let us experiment and find out. Mathematically we'll find out. So theta naught equal to 0, theta 1 equal to 1. Let's put into this formula. Okay, so the formula is, this becomes 0, h theta becomes theta 1x. Okay, theta 1x. In this theta 1x, if we put 1 into x, so theta 1 slope is 1, x is 1. So my value is 1 for the first point, p1. For p2, the value is 2 into 1 is 2. p3 value is 3 into 1 is 3. All right, these are the predicted points. All right, understand, predicted points. So these predicted points we will put into this formula. All right, how we can put into this formula? So I'm directly putting without writing a formula. So let's say this is a predicted minus actual. So predicted is 1 and actual is also 1. Predicted is 1 and actual is also 1. All right, so 1. Y value is 1. X is an input, y is the output. So square plus 2 into 2 square plus 3 into 3 square. And don't forget 1 by 2m is also there, but the point here is it is 0. So there is no use of finding out. Ultimately it will become 0. So cost function, my cost function is 0. All right, my cost function here is 0. What does it mean, cost function is 0? Basically it implies that the difference, overall difference, and the average of all the difference is 0. All right, that means I'll try to plot one graph here. In this graph we'll try to execute in one side theta 1, that is x value, and in one side j theta 1. All right, j theta 1 is nothing but cost function. So I'll give some values, let's say 0, 0 0.5, 1, 1.5, 2. Okay, these are theta's value, and here 1, 2, 3. These are cost function. So in this theta 1 I took, so for theta 1 j theta value is 0. So j theta value is 0. So here it is coming as 0 in this point. Okay, as because it is, the difference is 0. Now here by this example we can understand that it is a global minima. Global minima in the sense the actual point, the best fit line which we can use to predict the output. All right, but let us assume that we are not sure whether it is the best fit line. So what we do is we try to change the theta value. So this time let us assume theta 1 equal to 0.5. all right, here we have assumed theta 1 is 1. Here we are assuming theta 1 as 0.5. 0.5 means what? So I am trying to create a line that is similar to 0.5. So it will come something similar to this. I'm only increasing 0.5. For 1 unit of x, I'm increasing 0.5 unit of y. So let's say point is here, and point is here, and point is here. So there is a difference. The actual points are here, and the predicted points are here. So what will be the difference? This is the difference. These are the difference between actual and predicted. All right, forget this line, forget this line. So this is the actual and prediction. All right, let us try to find the p1 value, p2 value, and p3 value. So p1 value will be this time 1 into 0.5 theta 1x, right? The formula is theta 1x. So now this time also theta naught is 0. Theta naught is 0, and h theta prediction value is theta 1x. So 0.5 into 1 is 0.5, 0.2 is 0.5 into 2, 0.5 into 3. So if you try to find out the answer, it will be something as 1, and here 1.5. And if you try to put it in the formula, this main formula, what you will get? You will get it as 0.5 is the predicted, and the actual is 1 square. Next is 1 minus 2 square plus 1.5 minus 3 square. All right, and we have to do what? 1 by 2m. What is m? 3 points are there, so basically it is 6. If you try to find out the average cost function, you will get is 0.58. okay, you can just calculate it. Here I'm directly showing you just to save some time. So you will get as 0.58. so for theta 0.5, my value is 0.58, so it will come somewhere here. Okay, 0.58, let's say. All right, the first time we found theta, j theta is here. Second time we found j theta is here. All right, till now it is not confirmed. So last value I'll be considering as let theta 1 be 0. okay, I'm considering theta 1 as 0 this time, and let's see. So p1 equal to 0 into something, 0 into 1, p2 equal to 0 into 2, p3 equal to 0 into 3. So everything is 0, and the formula, if you put in, it is 0 minus 1 square plus 0 minus 2 whole square plus 0 minus 3 whole square, 1 by 2 into 3 data points. So you will get the answer somewhere between 2.33. so cost function is 2.33 this time. All right, so let us fit. So if the theta is 0, it is 2.33. so somewhere the line is coming here, the dot is coming here. So like this, if you keep going on, and if you put all the values, try to change the value of theta 1, you will find one graph like this, that is convex in nature. This is what I was talking about. This is what I was talking about here. This cost function, it will give you a function that is convex in nature. So it will look like something like this, and your goal is to reach this minimal point. This is the minimal point. This is called as global minima. I'll tell you what is global minima and local minima. So for now, this is the global minima because this is the best fit line, right? So if the data points are here, my best fit line is this rather than the red line. This is the best fit line because it is trying to predict the test data correctly, okay, with zero error. All right, this is the best fit line. So here we will try to find the global minima. All right, so let's see what is global minima and local minima. So I'll try to show you using graph. In this linear regression, we will always find a global minima. So basically, as the function is square, our function will always be looking somewhat like this. So our global minima is, let's say, here. Global minima, how we can find? Where the slope is 0. At this point, the slope is 0. Slope equal to 0 means the line is something like this. All right, this is called global minima, the lowest point in the mountain. Okay, if you consider this as two mountains, this is in between the mountains, right? This is the lowest point. Okay, steep. All right, this is called global minima. Global minima. And what is local minima? In deep learning, when we study, we will find some kind of graphs like this, where it is having global minima, but there are a lot of local minima also. So once you get inside this, your gradient will also be, or your slope will also be 0. Slope will also be 0. So you can never reach this global because you will get stuck here. All right, our point is to go to a point where slope is 0. So this is our global minima and this is our local minima. All right, our aim in linear regression, this is for deep learning. All right, we have a lot of techniques to solve this, so we'll see this later. For now, we'll focus on this. This is for linear regression. I hope you are understanding till here. All right, now we have to find this particular point. So in this case, what I did is I tried to change manually, right? I was trying to change theta. Basically, I'm trying to change slope. So intercept, I'm considering the intercept is here, but I was trying to change the theta slope manually. First time I took slope value as 0.5, then second time I took the value as 0, and also I took as 1. Okay, and then I'm finding out, okay, 1 is the best one. But in reality, we can't check like this manually. We have to go through a mathematical approach. All right, we need one process where it automatically finds out, or let's say it will, if my point is here in the randomly, if we try to find a point, and if my cost function is here, it should automatically come at this point. Okay, we need to find that particular process, and that process is known as gradient descent. Okay, gradient descent. So basically, this is nothing but convex. This is nothing but convex shape where we need to find the global minima. All right, I hope you are understanding till here. So the process of finding the global minima. All right, let's understand that. So before understanding that particular case, first what we'll try to get is calculus. In this calculus, why we are using calculus? I want to find the slope at a particular point. All right, let's say my theta, I am here in this theta. In this theta, where is my slope? What is the slope at this point? I want to know that. Okay, so instantaneous rate of change. Instantaneous rate of change, when I say, one thing should come into your mind, that is derivation. You should be doing derivation. So let me go a little bit more deeper into maths. Derivation, it is, if you see the definition, it is nothing but instantaneous rate of change at that moment. Okay, instantaneous rate of change. If I explain you with an example, this is nothing but a road is there, a bike is going in a from point A to point B, it is traveling with a certain speed. Now if I click a picture at a certain point, at any point of time, let's say here at 3 seconds, when I click a picture of that bike, can you just look at that bike and tell me what is the speed? By just looking at the picture of a bike, can you guess, or can you tell me the exact speed it was at that point of time? No, it is not possible by just looking at the speed. But instead of this picture of bike, if I give you the picture of speedometer, where it is showing that particular speed at that particular 3 second, then we can understand, okay, this is speedometer. So speedometer works as derivation. Derivation means what again? Derivation is instantaneous rate of change. Means at a particular point of time, at a specific time, what is the rate of change? All right, this will be given to us by derivation. So it is very simple now. At this point, what is the slope? How I can find? Using derivation. At this point, what is the slope? How I can find? Using derivation. All right, so let me talk about this thing. So our approach is quite simple. What we'll try to do, we'll try to change the value of theta 1, and using that we will try to find the cost function. This cost function is nothing but error. Okay, how much error? And in this we have to change the theta 1. While changing the theta 1, first let's say randomly we'll pick one number, we'll pick one value, let's say 1. Okay, in that one, what is the error? So let's say my error is here. So like that, I'll see the slope of that at this particular point. What is the slope? So let's say slope is like this. Okay, so there are two types of slope. One is negative slope and one is positive slope. Negative slope means what? At this point, after this point, at the right side, the this steep is downwards. Okay, this steep is downward means this is a negative slope. All right, let's say one point is there where this slope is like this. That means at right side, my steep, this is pointing upwards. So this becomes positive slope. All right, this becomes positive slope as because my right side after this point is pointing towards upwards, and here it is pointing towards downwards. We have to see from left to right, okay, this is negative slope, this is positive slope. So if my slope is negative, we will move towards left side. So I will try to change the theta and increase the theta here. So if I increase the theta here, again slope is like this, so again I'll try to change the theta. So I'll come down here. So like this, if we change one by one, I will reach a point where it will reach this point. After that, it will stop changing. Why? Because the slope is 0 here. The slope is 0. It is not positive, it is not negative. All right, then you can ask one question like, is it sure or is it necessary that this line or this slope will come down to this point? The answer is yes, it will come down to a slope. An example I would say, imagine you are blindfolded and you are walking in a, you are going in a mountain. All right, now your aim is to reach the ground. So how you can reach the ground? You can't see, but all you can do is you can feel with your feet whether the steep is positive or negative. All right, so you can just check at that particular moment whether the slope or steep is positive or negative. If it is negative, if it is like this, you will go forward. Okay, if it is negative, if it is positive, you will go backwards. If it is negative, you will go front. All right, likewise at some point you will reach the ground. This is the exact intuition of maths, and this will be helped to us by derivation. So that's why maths is very important. At a certain point of time, at a certain instantaneous, what is the rate of change? Rate of change means what is the slope? Here rate of change is nothing but slope. All right, so I hope you have understood positive slope and negative slope, and you have understood this is called global minima. It will automatically come down to this global minima. It is all defined by our formula, cost function and hypothesis. All right, so this thing, everything happening here, it is defined by gradient descent. Okay, it have one formula. Let me write down the formula. So theta can be theta 0 or theta 1. Theta 0 means intercept, theta 1 means slope. All right, so this is old theta. Let's say old theta, whatever theta I am assuming. So old theta old minus alpha. Alpha is the rate of change, rate of learning, how fast you are moving. Okay, means what? From here directly you can jump to here, or you can move slowly. So how fast it will change, it will be defined by alpha. So again, next is derivation of theta of j means whether it is slope or whether it is intercept, according to that, j of theta, this is nothing but cost function. All right, this is the formula. This is my actual formula which we will be using. So logically it is nothing but the old theta, what is there, from that old theta we will be subtracting, minus will be subtracting with the alpha, that is rate of learning, how fast or how slow we want to go, we will use that alpha. Basically we take alpha as not so big, not so small, let's say 0.1, all right, or 0.001. Like this we'll be taking one value, we can also change the value according to the scenario. So this main thing is nothing but derivation. This is derivation. This we need to find out. Rate of change. Rate of change. Alright, this we need to find out. So I will find out this using mathematical formulas again. Just hold on. We need to understand this. So this derivation, we need to find derivation. So one point is missing out. This minus, why we are doing minus? If you see minus, so let's assume theta 1. So theta 1, let's say 2, and here old is theta 1 is 2. This theta 1 we are doing minus and alpha, let's say a small number, into, let's say it is negative slope. Negative slope means what? The value will be negative, right? Negative 2. So if we multiply it, negative negative, it becomes plus. So some value, some small value. So here it becomes, ultimately it becomes plus. So that means from the old theta we are adding some value, so it will come this side, ultimately it will come this side. All right, that is what we use negative. So imagine one more, 2 theta 1 and minus, this time it is positive slope, so positive slope is positive value, right? Let's say 2. So if you do this 2 minus 2, it will be always reduced. So this was the previous value and this is the current value. So if this is the point is here, it will come down, it will reduce this side. Okay, this side. So this formula represents the movement, whether it should move left side or towards left or towards right. All right, but now we need to find the derivation. So let's find out derivation. So this derivation we need to find with respect to two things, that is theta naught and theta 1. All right, derivation of theta I, this we need to find out, same value, prediction minus actual and square. All right, let's find out the derivation. After that we will see how to proceed. All right, so one by one we'll try to find out. First we'll try to find out using theta naught. Theta naught is nothing but intercept. All right, so if we try to find out derivative of theta naught, so if you try to find out derivative of theta naught, let's do it. So d of theta naught and this whole thing, okay, this whole thing. So if you do this whole thing, what you will get, so let's assume this as u. Okay, I'm just assuming. So this u is prediction minus actual whole square. So something whole square, if you do derivation, what it will become? 2 and then derivation of this, right? This is a simple formula where we use, let's say x square. X square becomes what? 2x d of d theta of x. All right, likewise what we do is, first we take this 2, here it will become 2 1 by 2m, let's take it outside, d of d theta naught, 2 of prediction minus actual, and then d theta naught of again prediction minus actual. All right, so if you do this, you will cut out this 1 by m, and p minus a, it will come outside, it will come outside. So after derivation, I'm telling, after derivation it becomes this. All right, and then this p, what is this p? This p is, if you try to calculate, this p was nothing but h theta, right? So this h theta is nothing but, again it is theta naught plus theta 1x minus a. So if you do this with respect to a, it is constant, so it will cut out. Here also theta, this is also constant, it will cut out. So basically if we do theta of 1, it is constant, right? We cancel out. So all these are constants, so we can ignore that. Here theta 1 and theta 1, so it is dx of dx, what it becomes? It becomes 1. All right, so this is also 1. So my actual answer is prediction minus a into 1. All right, with respect to theta naught. With respect to theta 1, what it becomes? It becomes, let's derive it, 1 by 2m. So again same thing will happen to u. What is u? P minus a into d of d theta of this thing, theta naught plus theta 1 x minus a. So this time you see, check out, 2 cancel, 1 by m, p minus a is prediction minus a. Here square will not be there because square will come down, into theta naught, this is a constant, theta 1. So theta 1 it will get cancelled, it is 1. Now x is there, so that x will be coming here. All right, this is very important with respect to theta 1, and this is with respect to theta naught. Okay, let me write it clearly here. Derivation with respect to theta naught, it is 1 by m summation of prediction. What is prediction? It is h theta naught, h theta of x of I minus y of I. This is for h theta naught. For with respect to theta 1, this is derivation. So it is nothing but 1 by m summation of 1 to m, same thing, h x of I minus y of I, but this time here x will be there. Okay, as because x was there. All right, so this is the main formula. We will use this formula when we try to find the slope at any particular point while we change the value of theta naught and theta 1. All right, this is very important. So we have derived the formula, let's now use it so that we can understand again how this works. So again, this formula is also important. This is the formula, actual formula to find gradient descent, but this we have derived here. Okay, if it is theta 1, then use this. If it is theta naught, then use this. Okay, so let me write down the gradient descent formula again. So the gradient descent formula is for gradient descent with respect to theta naught and theta 1. So for theta naught, it is theta naught minus alpha of d theta naught and j theta, that we have already found out here. This one, and for theta 1 minus alpha of rate of change of theta 1 with respect to theta and theta 1, theta naught, this is also theta naught and theta 1. All right, here we'll be using this formula. All right, this is a gradient descent formula, and this formula is derivation of both the changes. So don't get confused that much. Here it is simple that when we change the intercept, this we will use. When we change the slope, we'll be using this. This is for slope and this is for intercept. Think in this way. Okay, don't get too much confused what exactly is happening or not. This is for intercept and this is for slope. So now let us assume again. Okay, all we do is assume. So what we do is, first we take data set as 1 by 1, 2 by 2, same data set we are taking, and let us try to find whether it is going positive or negative. Okay, so let me draw a graph here. This is theta 1, with respect to theta 1 we'll find, and this is cost function. So here it is x1 y1, x2 y2, and x3 y3. All right, in this what we try to do is theta 1, let us assume theta 1 as 1. Okay, theta 1 as 1. So in theta 1, what we find out, theta 1 means what, or let's say theta 1 is the perfect line, right? So once it reaches theta 1, it will not move. We know that. But let's do it using theta naught equal to 0. When theta naught was 0, if I show you the diagram, when theta naught was 0, it have to move this side, right side, right? From left to right, it have to move. So let's check how we can use this gradient descent in order to move from left to right. This is gradient descent formula. So here, when theta naught equal to 0, all right, let's keep all the values and check whether it is moving left side or right side. All right, so theta 1 value is 0 for point 1. If we try to calculate, theta 1 is 0 into x1, 1 minus predicted actual value is 1, and this theta 1 formula is nothing but here x is there, so x here is 1. All right, so if you try to find out this, you will get -1. All right, for point 2, 0 into 2 minus 2 into 2, it is -4. Point 3, 0 into 3 minus 3 into 3, we will get -9. All right, so this value we have found out. You sum up all the values. So if you sum up, sum is -14. So the whole thing, the value of sum is 14. So let's try to find out at this point what we are finding. We are finding the slope as j theta as slope means what? This value we have found out, the value of this. So this value sum is -14. All right, now let's put it in this formula. If we put it in this formula, it is the previous theta was 0. So the previous theta was 0, 0 minus rate alpha, let's say 0.1, into what is the gradient? Gradient we found out as minus. So this sum is 14. If we divide it by 3, how many points? 3. You will find out the average as minus 4.66. All right, this minus 4.66, this is the gradient descent, right? This gradient descent will put it here into minus 4.66. all right, if we try to find out the answer, it is nothing but 0.466. so this is very important observation. What is this? This basically means our theta was 0. I randomly chose theta as 0. So from this theta, let's say my theta is here, I have to move with this rate of change. So it will come down to 4.6. Let's say it will increase. Increase means what? It will go this side. Okay, it will come down this side. So it shows me a direction, which side to move. Okay, this is represented by gradient descent. This formula is very important. If it is a negative slope, so if my theta is somewhere here, it would tell me to move this side. Okay, it will reduce the theta value. All right, this is how it moves. So I hope you have understood this. Next, we will be looking at R square and adjusted R square. So now we will see two performance metrics. So what do you mean by performance metrics? Performance metrics is nothing but a way by which we can see whether the model is performing well or not. All right, it is quite simple. So there are two performance metrics, that is R square and adjusted R square. We will look at both of it by looking at with an example. All right, so R square and adjusted R square. So first of all, R square simply determines how much the model is working fine with. All right, how much percentage it is giving me a correct assumption. All right, so let's see R square formula. First, let's see formula. The formula is SSE divided by SST. What do you mean by SSE and SST? So SSE is sum of squared errors. So these all are errors. Again, I'll tell you what exactly is this. Next is sum of squared total sum of squared total sum of squares. So again, this, what is this SE and SSE and SST? So SSE is nothing but summation of yi minus y cap square, and here it is summation of yi minus y dash square. We will look exactly what is this, and by using this formula we will try to find out how much correct is our model. All right, so this is our formula. This is our formula. Let's take an example. All right, and why do we use r square, that also we will see, and when to use adjusted r square, that also we perform. So this y hat, what is this? I'll tell you with an example. So let me assume some data. First of all, let's say house A, B, C, and the actual prices are actual prices predicted, and something here, one column will come as average. All right, average of actual. So here let's say 100k, 200k, and 150k are the actual. Predicted is 110k, 190k, and then 150k. All right, this is predicted. The average, if you find the average, it is 150, 150k, 150k, and 150k. All right, so now let's calculate one by one. So let's calculate SST first, and then we will calculate SSE. So what is SST? SST is nothing but total sum square. So actual minus average. All right, actual minus average. This is nothing but average. So let's try to find it. 100, actual is 100 minus average square, plus actual is 200 minus 150 square, plus 150 minus 150 square. If you do this, you would find the answer as 5000. All right, you would find the answer as 5000. You can calculate it. Next, we will try to find out SSE. Okay, SSE, that is nothing but sum of squared errors. So this is the formula. What is y cap? We will see that. So y, this is actual minus y cap square. So actual is 110 and predicted is, this is y cap, predicted is 110. 110 square, this is 100, plus 200 minus 190 plus 150 minus 150 square. So if you try to find out again, the answer would be 200. All right, here it is 500, here it is 200. So let me find r square. R square is 1 minus SSE, that is 200, divided by 5000. So you would get something like 0.04, and in percentage 0.96, and if you convert it into percentage, it is nothing but 96 percentage. All right, that means this particular model, actual and this predicted, is working quite well. All right, this is known as, this is how we are going to find the metrics, performance metrics, whether it is performing well or not. So here we are finding it as 96. How we predict? Basically, we are comparing with the mean. All right, what does it mean? What does it mean? Let's say this is a price and this is a straight line. All right, this is the best straight line. Now we are comparing this and with the average one, let's say mean one. Okay, so according to the mean, compared to the mean, how much better it is performing, that is what it is being checked. All right, this is nothing but average. Average means, let's say this average of all this, you can somewhat find like this. So this one and this one, how much it is performing better than the average. So it is being checked, and here the answer is 96%. All right, this is how you can find out r square. Now let's come back to adjusted r square. How you can find out adjusted r square, and when to use adjusted r square? That is a bigger question. That is a bigger question, when to use bigger adjusted r square. Now one thing you will look at, that r square can be tricked. R square, you can make some mistake. Means what? So see here how many, let's say, features. So in this above, let's say 3 features were there. 3 features were there. According to 3 features, we are getting r square as 4. let's say 96. Okay, 96 percentage. Now if we increase the features, this r square will increase little bit. All right, it will for sure increase. That is what this particular formula says. It will always increase with the increase in feature. But the actual question is this feature that we are adding, is it really useful? Is it really useful in helping us to get a better prediction? So for example, let's say I'm buying a house and there one more feature is added, whether there it is male or female is staying in that house. So it is nowhere related to house pricing, right? But somehow it is increasing the percentage. All right, so from 96 to 97 it is increasing. So you would think that okay, this particular feature is directly related to house. So this is how r square can be tricked. So for that reason we have something called adjusted r square. So adjusted r square, the purpose of adjusted r square is called is to have a better selection of feature, whether it is useful or whether it is contributing in getting a better best fit line. All right, that is the whole point. So r square, adjusted r square formula, let's write it down. So the formula is 1 minus r square m minus 1 and m minus n minus 1. All right, this is the formula of adjusted r square. What is m here? M is number of data set and n is number of features. All right, so here I'll just tell you the gist of how exactly it shows or it tells us whether to use adjusted r square or not. All right, so imagine in this case, at first case and second case. All right, first case and second case. So first case and second case. In the first case, what we did is we had two features and we try to find r square. In that case, the r square, let's say it is 96%. All right, and once we increase the one feature, let's say we are using three features. So if this feature is useful to us or it is contributing towards getting a better best fit line, then what adjusted r square will also be somewhere near to the prediction, let's say 95%. All right, somewhere it will be near to that r square. But in case, let's say in the second case, two feature it was there in the beginning, let's say r square is 96. All right, after that we are increasing a feature that is not at all directly related or correlated, you can say. All right, no, correlated is different thing. So here you can say that the feature is not contributing directly, but somewhere it is increasing the r square, right? Somewhere, let's say it is increasing r square. So what you will do, you will try to find adjusted r square. In this adjusted r square, you will see a huge drop in the value. That means what? You will find something like 80%. All right, if you compare this one and this one, then what you will see that you will understand that this particular feature, when you have added, it is adjusted r square is increasing tremendously. So in that way we understand that this adjusted r square this feature is not that useful to us. So after you remove this feature and again you try to measure the adjusted r square, after you remove this feature and you try to find adjusted r square, then you will see the increase, let's say 96%. All right, that is how it works, r square and adjusted r square. So how it works, let me just show you here. So imagine this formula. Look at this formula here. N is nothing but number of feature. So if the number of feature increases, so let's say for two features r square was, so here also r square is directly related. Okay, this r square will be directly contributing. So for two features, if r square is 96 and adjusted r square is, let's say, 97, then here when you increase the n to 3, then let's say the previous one was 96, but when you increase this to 3, then adjusted r square will decrease it, because from the previous value what you are trying to do, you are decrementing. So the more it will increase, the more the whole denominator will be decreasing. All right, so this n is increasing means this will decrease. All right, the whole thing will decrease means this whole will increase. If it is increasing, then 1 minus some increased will be smaller. So in that case, the adjusted r square will be 86, let's say. So that is how you can find out that that feature that you have added is not at all useful. So you can try to avoid that feature and try to add some more other features that are useful. All right, this is a way by which r square and adjusted r square are used. So here you need to remember these two formulas. Two formulas are very important. One is r square. R square formula is this: 1 minus sse and sst. This is nothing but actual minus y cap, and here actual minus y dash, mean. This is mean and this is the prediction. All right, here r square, adjusted r square, how you find? The formula is 1 minus r square m minus 1 m minus n minus 1. All right, I hope you have understood r square and adjusted r square. These are performance metrics. Now after performance metrics, we'll try to understand a term, very important term in machine learning, that is overfitting and underfitting. And we'll try to see how we can overcome this overfitting also. Underfitting. So what is overfitting and underfitting? So let me give you an example. Let's say this is a graph. In this graph, let's take an example of test data. So these are test data, and we have predicted a line like this. So in test data or in training data, all right, these are training data. While we are training, we are passing all this training data, right? So while we are passing training data, this data or this straight line is performing very well with respect to the training data. But what if I pass one test data which is here or which is here? Then it is not doing well with the test data, right? It is doing well with the training data, but it is not doing well with the testing data. So this case is known as overfitting. This case is known as overfitting. All right. So model gets well with training data. It is also known as low bias. Low bias. All right. With respect to training, if it is coming, it is known as low bias. Now model does not perform well with testing data. Does not, then it is high variance. So if it is with respect to training, it is known as bias. With respect to testing, it is known as variance. All right. So this condition is known as overfitting. Model performs well with training data means low bias. This bias is a training. It refers to training, and variance refers to testing. It is high variance. Bias and variance, you can think it as difference, kind of. In simple word, it is difference. So with the training data, it has low difference. All right, the difference is very low. That means it performs well. But in variance, it is also a difference, but it is high difference. All right, high difference means not performing well. All right. Likewise, underfitting. This is overfitting, underfitting. In underfitting, what happens is model does not perform well with does not perform well with training, as well as model does not perform well with testing. So here also high bias and high variance, both are high, right? So this case is known as underfitting. I hope you are understanding. So let me again write it down, the models, three models, let's say. So model 1, model 2 and model 3. In this three model, first case is testing. This is This is training and this is testing. Training, testing, training, testing. So first model performs well with training and also performs well with, does not perform well with testing. So this is called as overfitting. Here training it performs well and as well as testing it performs well. So it is called generalized model. Generalized model. And in this case, it is not performing well with training and as well as testing. All right, underfitting. So here it is low bias and high variance. Here it is low bias and low variance. Here it is high bias and high variance. So these terms are very important in machine learning, especially in order to train the model and after training whether it is low bias, high variance. So make sure you understand this part. Next topic is we have something called R2 regularization. Regularization. This is also known as rich. So rich when we will use this to overcome overfitting. This overfitting problem when it is exactly intersecting the error, intersecting all the points that are used in the training set. So let's say this is a graph and these are the training data and my predicted value is here. All right, my predicted line is here. So if you see the cost function, what will be the cost function of this? The cost function will be exactly 0 because there is no error. There is no error. If there is no error, the cost function will be 0. All right, so basically the formula is 1 by 2m prediction minus actual whole square, right? So it is y hat minus y I whole square. And the formula, what is the formula of ridge? The formula of ridge is with this error you add a hyperparameter called lambda slope square. So this is the formula of ridge. So how it helps, let us see. So in this case we are getting this value as 0 as because it is exactly intersecting all the points, right? So now if testing data comes here, it will not perform well with the testing data, right? Because it is overfitting. It has learned so well with the training data that it will not perform well with the testing data, right? So in order to reduce that, we have introduced something called lambda slope square. So in this lambda slope square, what we do, so in this h theta of x, we know the formula theta 1 plus theta naught plus theta 1 of x, right? So we'll try to change the theta 1. So basically what we'll try to do, we'll try to make this slope little steeper, little less steeper. Okay, we'll not directly put this all this. Let's say a small change will do in this. So let's say like this. Okay, a small change. So if you change it small, then this slope will also change. If this slope changes, then the actual and the predicted data will also change. So let's say this value this time, once you change this slope, it is less steeper now. So what you will get is you will get a small value. So earlier you were getting a 0, right? So this time you won't get 0, you will be getting a small error. So that small error plus lambda, let's take it as 1. So 1, and let's assume that this is a theta is 2. So in the first case, let's calculate this. In the first case, let's say this is 0 plus 1 into 2 square. All right, this value is 4. This is for overfitting. This is for overfitting. The cost function is 4. So now this 4, we need to reduce it, right? Our main goal is to reduce the error. So this is 4 now after adding this slope when we are having the steep line. Okay, so now after this what we did is we changed the slope. So earlier let's say this was the prediction. Okay, while prediction the slope was steep, so we found out 2 square. All right, so after changing the slope, what we found out that there will be a, so after changing this time, we will find this error a small value. Okay, a small value will find, it will not be exactly 0 because we have changed this slope. So while we change the slope, it will be giving me error. So a small value plus lambda into, so slope is decreased here, right? Here it was increased, so this slope is little bit decreased. So when we decrease the slope, it will be, let's say this time 1.5 square. Earlier slope was 2 square, this time it is 1.5 square. So what will be my value? A small value plus 1.5 square is 3, so it will be somewhat similar to 3. All right, so this time it is little bit decreased. So earlier the error was 4, now the error is similar to 3. Again here I'm taking it as small value because this we will change little bit. All right, not a big change we will do, we'll do a small change in which we will get a error, small error, and with that small error we are changing the slope, and once we change the slope, we are getting that our model will now perform in a generalized manner, that is low bias and low variance. Earlier it was having low bias and high variance. Now with the help of ridge, that is L2 regularization, what we did, we didn't keep the slope, all the points we didn't keep it intersecting. What we did, rather than intersecting, we changed the slope little bit and made it in such a way that even if the testing, even if some data comes here, then it will also perform well in the case of overfitting. Rather than overfitting, it will play a generalized role. All right, so low biased and low variance. I hope you are understanding. So now let's see L1 regularization, that is lasso. This is ridge and this is lasso. So L1 regularization. All right, so let's see what happens in L1. So earlier we saw the formula was lambda slope square. Lambda is a hyperparameter. So how fast we are changing, that is defined by lambda. So in this error plus lambda mode of slope. Earlier what we were doing? Earlier we were doing square. Here you are saying we are using square, slope square. Here in this case we are using mode. So how this helps us? So this helps us in feature selection. How this helps us in feature selection? Observe it. So in our case, we just assume that one feature or two feature, right? So imagine a model where this is the y hat is having, or a model where we need to predict an answer from many features. So let's say theta naught plus theta 1 x1 plus theta 2 x2 plus theta 3 x3, like that, theta n xn. All right, so there are many features. So out of these features which are important, that we need to select. All right, all the features will not be important for sure, so we need to select. So while in ridge, what we were doing slope square. So what the slope square does, it increases the value. Okay, it multiplies the value. But here in lasso we won't do squaring, rather than that we will just take the mean of it. How we do that? We will just take the important features that should be taken. If it is too small, we'll just neglect that. So for example, let's say one theta is 0.01, and let's say one slope is 20, or let's say 2, or let's say 3. So these two features will be taken and this feature will be neglected. All right, so in this way it helps us to do feature selection. All right, so ridge and lasso, how it helps us to prevent overfitting, and second, it helps us to do feature selection. So this is very important from the interview point of view, that they will ask you that how ridge and lasso helps us. So ridge helps us to prevent overfitting and lasso helps us to do feature selection. So there might be n features, which one is important, which one to keep it, you need to decide it. So what is the formula? The formula is error plus lambda of slope mode. all right. In here it was lambda of slope square. So I hope you have understood this particular algorithm of linear regression, and if you have liked it, don't forget to subscribe the channel and help me out to grow this channel. I am putting a lot of efforts and I want to give more content like this, but the problem is if I don't get the views or likes or whatever, it does not give me that motivation to keep going on, right? So if you are liking it, make sure you share it with your friends, and that's it. I'll bring more of algorithms in the next videos. Thank you.